Alright, hey guys, I just wanted to do a hopefully quick video on how to show and prove maximum power transfer. Now when I say maximum power transfer, that means getting the most amount of power delivered to your load depending on your voltage and the internal resistance of your voltage source. So the first step is to Thevenize your circuit. And if you don't know what Thevenin's theorem is, well, that's another story and a different topic, and I'm not going to explain that right now. But basically, the basic of Thevenin's theorem is to take any kind of circuit you have and break that down or simplify that circuit into a single voltage source, a single internal resistance of that voltage source, and then whatever your load resistance is going to be as well too. So just to start off, we'll do a real simple series circuit with a DC load coming over to a resistor. Now this resistor is going to be the resistance of your source, so we'll mark that RS. Source resistance. Just lost some light. And we'll continue on. Jeez. And place another resistor here. And this is going to be our load resistance. So we have your voltage source, the internal resistance of that voltage source, and you could almost imagine this section right here as a battery or even a voltage source. Let's make this a positive 10 volts, and let's just say for demonstration purposes that the source resistance is going to be 5 ohms. Pretty simple and straightforward. Now what the load resistance for the demonstration is going to be variable. And by varying that load resistance, it will show the maximum amount of power that goes through that load is when this load is at 5 ohms, basically matching the source resistance. So to start doing this, I just use simple Ohm's law. The first step is to figure out a formula for current. So we can have E equals I times R. Pretty simple and straightforward. Now we already know what E is, so we can fill that in. 10 volts equals I times. Now for R, since this is a real simple series circuit, R is going to be the combination of these two. So we're going to have RS plus RL. So now we have 10 volts equals current times RS plus RL. Now, if we want to get I by itself, simple algebra, and we have I equals 10 volts over RS plus RL. So now we know a formula to figure out the current. So now on to power, which is the most thing that we're concerned about. And all we're concerned about is the amount of power that's going through our load. So we can use Ohm's law again, where power for our load equals I squared times R. Again, real simple, basic Ohm's law. We already know what I is. I is 10 volts over RS plus RL. So we can have P of our load equals 10 volts over RS plus RL. Since it's squared, do it again. 10 volts over RS plus RL, and then multiply by R. And this R is going to be our load resistance. So L and L. Everything is going to be concerned about the load because obviously that's what we're trying to drive. So here is where we start calculating the resistance. Let's just make this a real simple 1 ohm load. We can come in here and plug all this into our formula that we already know. So the power of our load is going to equal 10 volts over 5 plus 1, so 6. Do it again. 10 volts over 6 times, since this is RL, times 1. Right, so basically we have P equals 10 over 6 squared times 1. Do that on the calculator real quick. 10 divided by 6 is 1.6 repeating. Square that, and you have 2.7 multiplied by 1. That's pretty simple. So P of our load, load of our power, the amount of power going through our load is 2.77 watts at 1 ohm. 2.7 watts. Okay. Let's increase this load to 2 ohms. So now our load resistance is 2 ohms. P of RL equals 10 volts over 7 ohms times 2. 10 over 7 is 1.42. Square that. Don't forget the square. Square that is 2.04 times 2 is 4.08. So power of our load equals 4.08 watts at 2 ohms. Now we can see that's a pretty significant increase in power from 2.7 ohms to 4.08 ohms, and that's only an increase of 1 ohm. So we'll keep going up. We'll increase this load resistance to 3 ohms. And now we'll plug that in down here. P equals 10 volts over 8 ohms squared times 3. PL equals 10 over 8 is 1.25. Square that, and you get 1.56. Multiply that by 3, and you get 4.68. 4.68 watts at 3 ohms. Alright, so we're still keep going up in power, which is good. We want the most amount of power transferred. Let's increase this load resistance to 4 ohms. Plug that back in down here. PL equals 10 over 9. Square that times 4. Do that real quick. 10 over 9 equals 1.1 repeating. Square that, and you get 1.23 times 4. You get 4.93. PL equals 4.93 watts at 4 ohms. Alright, so we're still going up in power, which is good. Let's increase this to 5 ohms, which is the matching resistance of our source resistance. PL equals 10 over 10 squared times 5. Well, 10 over 10 is 1. Square that is still 1. Multiply by 5. So, power of our load equals 5 watts at 5 ohms. There you go. 5 watts at 5 ohms. That's pretty good power. Let's increase this to 6 ohms, which is obviously going to be over our matching resistance. Starting to run out of room here. PL equals 10 over 11 squared times 6. 10 over 11 is 0.90 repeating. Square that, and you get 0.826 times 6, and you get 4.95. So P over L equals 4.95 watts at 6. Whoops. Not 65, 6 ohms. And you can see that the power has obviously decreased from what our 5 watts was at 5 ohms. So just for the last demonstration, we'll bump this up to 7 ohms. We'll do PL equals 10 over 12 squared times 7. 10 over 12 is 8.3, I'm sorry, 0.83 repeating. Square that, and you get 0.694. Multiply that by 7, and you get 4.86. So power of our load equals 4.86 watts at 7 ohms, which is still decreasing from what our 6 ohm power rating was at 4.95. So as you can see, as we increased the resistance from 1 to 4 ohms, the power increased until we got up to 5 ohms and we got 5 watts. And then once we increased past 5 ohms and we got to 6 and 7 watts, you can see that the power is starting to decrease as well too. And they're almost pretty close to plus or minus of whatever our maximum power transfer is. So plus or minus 1 and you got about 4.9 watts, plus or minus 2 and you get around 4.7 watts. So there it is on paper. I hope that was pretty simple and straightforward. So the next step that I would like to do is show you in Excel how it all works by plugging in some of the numbers and then throwing up a chart and getting a visual representation of how it all works. So let's go to that.
Alright, so I wanted to show you real quick here in Excel how to calculate this out and get a visual representation on a graph. So let's start with our load resistance, and that's 1, and this is going to equal that plus 1. We'll go down to 20 ohms. Okay, and now this is going to be our load power. And just for the heck of it, let's do load current, even though it's irrelevant. Over here, we're going to have our voltage source and our source resistance. Source resistance. Let's use the example we just used, 10 volts. 5 ohms. Okay, so here is where we want to enter in the formula that we're using, where P equals I squared times RL, which is our load resistance. So Excel can get kind of touchy, so let's hope we do this right. So equals, parentheses, our voltage source divided by another parentheses, RS plus RL, close your parentheses, close them again, and then you want to multiply and do the same thing over again, where it's basically M3 divided by parentheses RS plus RL, close the parentheses, close them again, and then multiply by RL again, and close the parentheses. The other thing that we want to do is we want to make sure that our voltage source and our source resistance gets locked. So as we drag this down, it'll follow this down, but these two will stay stationary where they are instead of incrementing down as well too. So by doing that, we use the dollar symbol, and we want to use it on anything that has an M with it. So dollar symbol, that, and that. We'll hit return and see if Excel likes this or not. Look at that, and it took it, and look at that. We have our 2.77 watts of power. Now hopefully we can drag this down and have it increment up, drag it down again, and by doing this, it is following the load resistance as it goes down, but it's keeping these two where they are. Oops. So we'll just continue to drag this down all the way to 20 ohms for our load resistance. Select these all and move the decimal place over to hundreds. And like I said, we'll just do current real quick since we got both. Current is going to equal our total power divided by our voltage source. And we want to go back in and lock our voltage source in, hit return, and we'll pull that down as well. And so what you can see here is that, well, just about the same thing we saw on the pencil and paper, is that our load resistance increases until we get 5 ohms at 5 ohms and 5 ohms, which is matching resistance, and we have a total of 5 watts, and then it starts to decrease from there. And same thing as the current, even though since this is a Thevenized circuit and it's a series circuit, the current's going to remain, but this just shows that the current goes up too. Now another cool thing that I wanted to show you in Excel is that we can plot this out on a graph, and we'll do a scatter graph with lines. And get the text in here as well too. And scatter graph with lines. And yes sir, that is right. And so basically what this shows you is you have your resistance, your source resistance on the x-axis, and then you have your power or your watts on your y-axis. And at 1 ohm you got a little under 3 watts, which is right here, 2.78. And as the load resistance increases to 5 watts, you have a maximum of 5 ohms, you have a maximum of 5 watts, and then your power really starts to decrease as the load resistance starts to go up. You know, I'm not really liking how that all turned out. Let's see if we can get a better one here. Nope. Maybe I move this over to there. There it goes. That looks a lot better. Our load power with one single line. The other cool thing about Excel is that it lets you do real-time information. So let's say all of a sudden your voltage source changes. Let's say your voltage source went from 10 volts to 20 volts. Well, I guess that doesn't change too much, but it does change, well, as far as the maximum power transfer, but it does change your wattage for sure. But let's say your internal series resistance or your source resistance changed from 5 ohms to 10 ohms. And you can see that at about 10 ohms is where you get the most amount of power. 10 ohms, 10 watts. We'll go back down to 10 volts. 10 volts, 2.5 watts at 10 ohms. Where you can really see this drastically is, say you have a source resistance of only 1 ohm. You can see that at source resistance with 1 ohm and your load resistance at 1 ohm. Spell that wrong. R-E-S-I-S-T-A-C. you can see that it makes quite a big difference. Or say you wanted to go to the other end of the spectrum at 20 ohms, you can see that that's quite a big increase. So you can also do 10 ohms and have it there. So this is what I like about Excel, is that lets you interact with the numbers and really gives you a visual representation on how maximum power transfer works. So I hope this helped to better understand how it all works and why they always say you want to have a matching resistance of your source resistance with whatever your load resistance is going to be. So thanks for watching, and I hope it helped.